This video is for section 3.8, derivatives of inverse trig functions. Let's start with a review of how to get the inverse of a function. So we'll start with just a linear function here. So we've got 2/5 x plus 1. So this is a line. It's got intercept of 1 and a slope of 2/5. So up 2 over 5 is the slope. So to find the inverse of this, we start out by swapping the x and y. So we swap the x and y there, and then we go ahead and solve for y. So we bring the 1 over to the other side and multiply by the reciprocal there. And so we've got 5/2 times quantity x minus 1, and then we can distribute the 5/2, so we get 5/2 x minus 5/2. And that's your inverse. And so if we notice here, here's our inverse. We've got an intercept of minus 5/2. We've got a slope of up 5. So that's up 5 and right 2. And then if you notice the inverses, since it is a swap the x and y process, that means we can look at this from an ordered pair standpoint as well. Of inverse just being switching the x and the y coordinates. So if that's the case, then your inverse and your regular function have a line of symmetry, and that line of symmetry is y equals x. And that's, you can see that line of symmetry here. Think of that as a fold in the paper. So let's try then talking about inverse functions with respect to a trig function. So let's start with sine x. So here is sine x, and then if you remember, in order to find the inverse of a trig function, you have to take the domain where the function is 1 to 1, where there's exactly 1 x to 1 y, which means you have to pick part of the pattern that doesn't repeat. So you're looking at half of the pattern. So our 1 to 1 domain is from minus pi over 2 to pi over 2. And then let's go ahead and go through this. We're going to swap the x and y, and then we're going to solve for y. So solving for y involves taking the inverse of the sign to isolate y. So we get this, this expression that says y is the inverse sine of x. So if we swap the x and y, it's like taking this shape here and flipping it and rotating it. So our inverse looks like this. If you notice our this shape, then we can get by doing this. So graphically, what we're going to do is we're going to take this red shape here, and we're going to flip it, and then we're going to spin it, and that is the inverse function. And if you notice, its domain now is -1 to +1, which was the range of the original function. So again, that inverse is flipping the x and the y's. So the range here becomes the domain here. And so when we look at this, here's our sine function, 1 to 1. Here's our inverse sine function. And by 1 to 1, I mean it's a 1 to 1 function. So it goes from minus pi over 2 to pi over 2. And then here's our inverse sine function, whose domain is -1 to 1. And whose range is negative pi over 2 to pi over 2. So the derivative is not really intuitive like the regular trig functions. The derivative of this inverse sine function is this. So the inverse sine of x is 1 over the square root of 1 minus x squared. Let's also look at the cosine function. So we can go through the same thing with the cosine function here. Here's our cosine function. For the cosine, we're 1 to 1 in this region here. And so that's from 0 to pi. So we can swap the x and the y's here, and then we can go ahead and do the inverse cosine to solve for y, and we end up with this this graph, which if you notice, the domain goes from -1 to +1 here. So graphically, what we're looking at is Here's where that cosine is 1 to 1. And we're going to go through the same steps here. We're going to flip it, and then we're going to rotate it, and we're going to have this after we have the rotation, and that's going to be our inverse cosine function with its domain now -1 to +1, which happens to be the range of the cosine function. So looking at the cosine function, then here's our cosine function from 0 to pi, and when we take the inverse, that becomes the range. The domain here is from -1 to 1. The range here for this cosine function is -1 to 1. That becomes the domain of the inverse. Just swapping those x and y's. And again, the derivative is not really that intuitive. The derivative of the inverse cosine it looks a lot like the sine, but it's -1 over the square root of 1 minus x squared. So if we look at what the two inverse functions, like I said, they're not intuitive, they're not obvious. They actually can be found by implicit differentiation, but we won't go through that here. It's a little beyond the scope of the course. So the inverse sine is this. The inverse cosine, notice it's just the opposite or the negative of that. And then the next page, we're going to show you the 6 derivatives. And this is kind of one of the rare times where I'm just going to ask you to memorize them. And so when we're going to use these 6 derivatives, we're just going to practice taking the derivative of each one, and we're going to incorporate things like the chain rule as we do the derivatives of these inverse trig functions. So here are the derivatives of the inverse trig functions. Here's the sine that we did, the sine function that we did. And notice now I've changed the variable to u here so that we can go through the chain rule of taking the derivative of the inverse sine, and then the derivative of if we have an inside function here. So this is kind of a built-in chain rule here. The tangent looks like this: 1 over 1 plus u squared times du dx. And the secant's a little more complicated. In the denominator, we have the absolute value of u times the square root of u squared minus 1. And then the other three, the cosine we did, the inverse cosine we did in an example earlier, on an earlier slide. Here's the cotangent. Notice the cotangent is just the opposite of the tangent, just like the cosine was just the opposite of the sine. And you might have guessed it, the cosecant is just the opposite of the secant. So if you can memorize sine, tangent, and secant, then cosine, cotangent, and cosecant kind of come along for the ride here. Just a quick note, there's an alternative expression for inverse. For instance, inverse sine, we can write it as sine to the -1 of x. We also can write that as arc sine of x. So that's the two ways you'll see it represented, both in the homework and on tests and on the AP exam. So let's try this. We're going to do find the derivative of the inverse sine of 3x. So notice inside here we have an outside function, the inverse sine. We have an inside function of 3x. So we're going to have to use the chain rule here. So we're just going to call that y. And then let's just go ahead and call 3xu. So we know du dx is 3. And that way we can do the derivative of the outside times the derivative of the inside. So the derivative of the outside is this derivative of the inverse sine. So we have 1 over 1 minus the quantity 3x squared, all with a square root around it, times the derivative of 3x, which is 3. So there's the derivative of inverse sine of 3x. And then we can kind of simplify that a little bit. In this example, let's try taking the inverse tan of 2x squared. So again, I'm setting these up specifically for using the chain rule. So again, we'll just call that function y. And then we'll do a substitution on 2x squared. and set up the derivative of the inside here. So if u is 2x squared, that's the inside function, the derivative of that is 4x. And then we can take the derivative of the outside function, which is the inverse tan. So that's going to be this expression here. So 1 divided by the quantity 1 plus 2x squared quantity squared, and then times the derivative of the inside, which is 4x. So simplifying that a little bit, we have 4x over 1 plus 4x to the fourth. Just processing those brackets there for the derivative of the inverse tan. And then let's try a cosine example with a 1 over x as the inside function. So we have y equals inverse cosine of 1 over x. We'll do the u substitution of u equals 1 over x. Remember, that's x to the minus 1. So when we do the derivative there, it's going to be minus 1x to the minus 2. We can also write that as minus 1 over x squared. So when we can now use the chain rule to find the derivative here. So it's minus 1 divided by the quantity square root of 1 minus 1 over x squared times minus 1 over x squared, which is the derivative of the inside. And then simplifying that a little bit, we can just go ahead and put the x squared in the denominator with the radical. And then minus 1 times minus 1 in the numerator is positive 1. So the other thing we can talk about is taking derivatives of inverse functions just numerically. And so as a way of doing that, let's just kind of look at x squared. We look at x squared a lot. The derivatives of inverse functions, if we look at this, it says f is a differentiable function. So like x squared, for instance. And as long as the derivative is never 0, then f has an inverse. And that inverse is also differentiable. And so we're going to take a look at that inverse and the derivative of that inverse and kind of compare it to the derivative of the original function. So we're going to find a couple of things here. F of 2 is just the value of the function at 2. F prime of 2 is the value of the derivative at 2. So this would be like the slope. And then we're going to find the inverse of the function. And then we're going to find the derivative of the inverse of the function. So that would be the slope of the inverse. So let's take a look at those 4 things. Okay, here is y equals x squared. First thing we're going to do is evaluate it at 2. So we stick in 2 there, and we get f of 2 is 2 squared, which is 4. So we know that when x equals 2, y equals 4. That's all that's saying. Now let's go ahead and take the derivative of f. That's 2x. So that's the derivative. I say derivative, you think slope. So if I'm going to evaluate that at 2, I'm going to find the slope of the curve at 2. So my slope is also 4. And that just happens to be the same because 2 squared is the same as 2 times 2. It's the only number that happens for. So I have a slope of 4 on my original function at that location. So let's take a look at the inverse. For starters, if we want the inverse of this, we're going to switch the x's and the y's. So it looks like that. And then after we switch the x's and the y, we can solve for y. And I'll just reverse that there. And so I'm going to call that the inverse. So the inverse is the square root of x. So we can graph that over the same domain. Looks like we have the domain of just positive values of x. So we're going to graph the square root of x. It's going to look like that. And we can see the symmetry over that line of y equals x. And now what we're going to do is we're going to find the value of the inverse. Okay? And we're going to look at also the derivative of the inverse. So if this is the inverse, and we're going to rewrite the square root of x as x to the half power, then we can find the derivative of that. So using the power rule, we bring down the half, we subtract 1, so we get 1/2 x to the minus 1/2. So simplifying that, putting putting the x to the minus 1/2 back in the denominator and giving it back its radical sign, we get 1 over 2 times the square root of x. And this is just saying the same thing. So here's the derivative. Now let's go ahead and see where we're going here with the information for the value of the inverse and the value of the derivative. So in this case, we have to evaluate the inverse at 4. Remember, we're talking about the inverse here, which means we're swapping the x's and the y's. So if the original function was an x value of 2 and a y value of 4, then the inverse is going to be an x value of 4 and a y value of 2. So evaluating the inverse at 4, square root of 4 equals 2. So that is that point right there. And then evaluating the derivative at 4 means putting 4 in here, this expression. So 1 over 2 times the square root of 4. It's 1 over 2 times 2, that's 1/4. So the slope of the inverse is 1/4. So if we look at this, the slope of the original function is 4. The slope of the inverse is 1/4. So you recognize those as reciprocals. Okay? So that allows us to then conclude that if I know the slope of my function, I can find the slope of my inverse by just taking the reciprocal, or vice versa. So because x and y are reversed, to find the reciprocal function, that following pattern always holds. If I want to find the derivative of the inverse, okay, then it's the reciprocal of the derivative of the function at a, as long as I'm evaluating the inverse at f of a. So if I'm evaluating, so to kind of recap, if I evaluate the derivative at x equals a, and that gives me some f of x, then if I evaluate the inverse at that f of x, then it should be the reciprocal of the derivative of the original function. Okay, so kind of digesting this whole statement here, this first portion that says the derivative of the inverse of x, inverse of f of x. Okay, evaluated at a, evaluated at f of a, so that's like your y value, is equal to the reciprocal of the derivative of the function f evaluated at a. So if we look at a typical problem here, let's say we have a function, and when x is equal to 3, y is equal to 5, and at 3, the derivative is equal to 6. So we have this point 3 comma 5, and at 3 comma 5 we have a slope of 6. Okay, so what is the derivative of the inverse at 5? So notice we're evaluating the derivative of the inverse at the y value, because it's the inverse, and the inverse swaps the x's and y's. So if we evaluate the inverse at the y value, the derivative then should be the reciprocal of this derivative. So using that formula, then the derivative is 1 over 6. Okay, so at this point you can go ahead and open up WebAssign and work on your 3.8 derivative of inverse trig functions. There's only one homework assignment for this, so it's just that day 1. We'll be moving on to 3.9 at our next class period, and then make sure that you go back to 3.7 and finish 3.7, 3.6, and 3.5 and finish up anything that might need finishing there. You can look in Infinite Campus to see if there's anything missing. You can also look at your scores in WebAssign to see if there's anything that's under 100%. In addition, there is also a 3.7 Blackboard quiz if you'd like to try to test out a 3.7.